Good morning, everybody. My name is Lilian. I will present my article about food inflation during the COVID-19 pandemic, a comparison between Brazil and Thailand. Why did I choose this theme? I realized that Thailand and Brazil have many similarities. They both are significant food exporters globally. Trade balance in processed food and agro-based products, it was huge for the years of pandemic 2020 and 2021. For example, for food and beverage, Thailand had a net balance of 17 billion of US dollars, while Brazil 63 and 70 billion. And then I realized that although these similarities, the food inflation in Brazil started to accelerate and quick pace, while Thailand food inflation kept low and stable for the whole period. And here we can see that in 2020, in January 2020, the food inflation was pretty similar between these two countries, and starts to increase during the second quarter in Brazil, but the curve was quite flat here for both countries, but in the third quarter, the curve kicked upwards for Brazil and downwards for Thailand. At the end of the year of 2020, the cumulative food inflation in Brazil was 14, while in Thailand was closer to 0. In 2021, the same. In the second semester, the curve kicked upwards in Brazil, reaching almost 7% for the year, while in Thailand it's close to 0. And during the whole year, the monthly food inflation was below 0 in Thailand. So Thailand experienced food deflation actually. So my research question is, given all similarities, Brazil and Thailand are both developing economies. Both countries are food net exported. Both countries were hit by COVID severely. And why those countries had different outcomes in terms of food inflation? So, based on the literature review, I withdrew two important key variables that can explain this behavior. One, the domestic energy inflation. Another one is exchange rate. The social significance is because in the developing economies, food is a massive part of the consumption basket, and food inflation for households in breadline can lead to starvation. The price elasticity for poor households is high as well, and the expected benefits, the apparent dissemblance between these two countries might discourage study comparing these two economies, and also the lack of the literature to reinforce the importance of this investigation. The limitations, there is scarcity of literature compared to countries, and the scarcity of studies assess the food prices behavior during COVID, and the data scarcity as well. The period encompasses only 24 observations. Okay, the methodology chosen here was a time series. ARDL, autoregressive distributed lag. The ARDL was developed by Pesaro and Chen in 1999. It was chosen to perform two different models for each country because the panel data was not well developed for ARDL methodology, and also its simplicity with just one single equation for the whole model, and it's suitable for short time series, and also an encompassing can cope with a different kind level of integration. Even though the ARDL tackle time series integrating order 1 and 0, I have to check for unity rules, and I have to check for the stationary. What does mean stationary? It means that mean and standard deviation do not vary. The error term can be autocorrelated, and I have to check the presence of unity rules. How can I check this? There's a univariated equation here, so we're gonna focus on B3. B3 is the correlation, is the regressor that indicates the correlation between the dependent variable and its past value. So I take the first difference and I plug in B3 and C minus 1, for example. If C equals 0, then B3, if C equals 1, then B3 is equals 0. That means there's no relationship between the dependent variable and its predecessor. And so the hypothesis, null hypothesis B3 equals 0. The alternative hypothesis B3 different of 0. I use the Dick-Fuller test because it's reliable and popular. For simplicity, considering a variable time series, so yt is equal ρ1 yt minus 1. Then ρ1 have to be within the unitary circle. My hypothesis is the null hypothesis ρ1 is equal 1, and the alternative hypothesis ρ1 is less than 1. So I employed OL as regressor to estimate ρ, and if ρ1 is larger than 1, then the time series has an explosive behavior. If the ρ1 is equal 1, then the time series has unity roots, it's not stationary. And if ρ1 is less than 1, then the time series is purely stationary or integrated by 0. This is the RDL model. So this model is a P and Q model. The short run can be mathematically expressed as follows. This part stands for the autoregressive component. In other words, the dependent variable, the past values of the dependent variable. This theta is the coefficient of the past values of the dependent variable. That part here stands for the distributed lag component. The sigma here is the regressor of the explanatory variable, and this here, sigma 1 x t minus 1 is the past value of the explanatory variable. So therefore, these two models are relative to Brazil and Thailand. This stands for Brazilian food and beverage inflation. This part is the autoregressive component, and it was statistical significant for both countries for 1 month lag. And this part here is for Brazilian energy inflation 1 month lag. And I didn't have to do any transformation because it was purely stationary. And here is the same with 7 months of lag, which means that for Brazil model, the energy inflation hits food inflation in 2 waves. first one with 1 month lag, another one with 7 month lag. Here for the exchange rate, I couldn't use the exchange rate by itself, so instead I used the nominal effective exchange rate. And because the exchange rate by itself was not stationary, even with I had differentiated ones, and then I have to use NER, and I took the log form, and then the first difference to attend the assumptions of of stationarity and non-heteroscedasticity, error term normal distributed, and no autocorrelation and no serial correlation as well. But then I will interpret this differently. I will interpret this in terms of percentage growth and Brazilian nominal effective exchange rate. For Thailand, I had to introduce this control variable to achieve the model stability, and also the four main assumptions for the reliability of its coefficient, and this and be also statistical significant, and the sign also was as expected. This stands for Thailand agro production, and it's negative related to food inflation. And for Thailand, I have to differentiate the Thailand energy inflation, and then I will read that as growth. But the growth and the energy inflation impacts food inflation with contemporaneously and with 1, 2, 3 months. Then the impact of energy inflation is more spread for Thailand than in Brazil. In Brazil is more direct. And also it's more direct, and also takes a while as well. It spends like 7 months. For exchange rate, I have to do differentiation as well, and turns statistical significant the distributed lag of 1 month. Brazil autoregressive component has twice the magnitude of this equivalent in Thailand's model. The Brazilian equation displayed that each unit of positive change in energy at 0.14 and 0.12 to food inflation, with 1 and 7 months of lags respectively. For Thailand, this impact is more spread through the months, and for the exchange rate, in the Brazilian model, the coefficient of NER tells that each 1% change in nominal effective exchange rate growth adds 2.98 units in food inflation 7 months later. For Thailand, each unit of positive variation in the rate at which the Thai baht increase leads to a rise of 0.2 units in food inflation. In conclusion, during the pandemic, Thailand kept at a low level two crucial economic drives that can trigger food inflation. Domestic energy, for example, in the 2020, Thailand energy inflation was -60.7, while Brazil's was 8.8, and the exchange rate, whereas the Brazilian will depreciate by 30%, Thailand currency depreciate affected only 7%.